thanks very much. It's been great being at this meeting. I feel like a bit of an interloper because I'm not an expert on cosmology or black hole physics. But Charlie suggested I could maybe say something about this task called summoning, which at least has some relevance. It may turn out to be a useful way in these, addressing some of these foundational issues about where and when quantum states are in space and time. So I know it's a pretty mixed audience, and I apologize to everybody who's in, at the wrong ends of the spectrum for the talk. But who's already heard of summoning here? Summoning. So, yeah, substantial. Heard of, yes, the task, yeah. Okay. Okay. I'll be gentle, which was my plan anyway. So this is, and sorry for some of you who may actually be familiar with pretty much everything I'm going to say. So there's a sort of geekish way of trying to think about quantum field theory or relativistic quantum theory or quantum information in space-time, which thinks about inputs and outputs and whether and tasks based on them. So the general, I'm going to specialize, but the sort of general version of this would be something like this, that nature is going to give you at various points, let's call them PI, inputs, and they could be classical information, they could be quantum information, they could be a mixture. So these red things are coming at you, and you know nothing about them until the point P. And you, by the way, I'm not a single individual in this way of thinking about things. You're part of a collective, an agency that's distributed through space and time. So I'm going to talk about you or Alice or Bob, but I really mean this large agency that could have agents sitting at all these points. So they're able to receive the inputs, certainly. They could, and they maybe know in advance what the points are. They could have agent stationed there. But their task is to produce outputs at another set of points. And again, the outputs, these blue things, they could be classical information or quantum or a mixture of both, depending on the task. And the outputs are supposed to depend on the inputs according to some algorithm that you know in advance. So the general question for any task like that is, given that you know the points in advance, but not the inputs, and you know how the output points in advance, and you know how the outputs are supposed to depend on the inputs, is there some way, and you have unlimited resources and instantaneous computing, you don't have any technological problems, but is there any way, according to the laws of physics, that you could guarantee to satisfy that task, assuming you've distributed all the entanglement you want anywhere you want and set up appropriate gates everywhere? So, in general, we don't know, but we could try and think about special cases where we can at least make progress. And I guess the hope is, if you think about enough special cases, you may learn the general principles that allow you to answer the question for the general case. The case I want to focus on here is the task of summoning. So, again, I need to stress, we've got not individuals, but agencies. Alice has got agents all over space who stick around throughout time. So does Bob. And then the agents don't overlap. There's never an Alice agent right on top of a Bob agent, but they can be arbitrarily close. And all Alice's agents are working together with complete trust and collaboration and whatever pre-agreement they need. So we're just going to call them Alice. Likewise, Bob. And Bob is going to make a quantum state, and in agreed Hilbert space, it'd be enough to think about a finite dimensional space and in some form that they've agreed in advance. And we might as well let it be pure. He knows it. He knows what he made. He's got a classical description of it. Alice doesn't know it. As far as she's concerned, it's just a Haar measure random state. And at some fixed point, Bob gives the state to Alice, so point P. And in the most basic version of summoning, well, there's some point Q that's going to be in the causal future of P, and he's going to ask for it back. He's going to summon the state there. So he's going to ask Alice to return it. So there's a terminological issue here, really. I mean, maybe the task isn't, at least according to Pedant's, perfectly named. because the summoning is really what Bob does, and Alice is supposed to respond to the summons, and the question is, can she do it successfully? And this issue was essentially discussed already in Henry IV, Part 1 by Shakespeare. So here we have a dialogue between Glendower up here, who says, I can summon spirits from the vasty deep, and Hotspur, who responds, yeah, so can I, so can any man, but will they come when you do call for them? And if you look at the critical reviews, they note that Hotspur's personality, which maybe is also well expressed in the painting here, tends to alienate his colleagues, and one can see why. But he does kind of have a point if one's literal-minded about it. So, nonetheless, we're going to ignore Hotspur, and we're going to call this task summoning, and when I say summoning is possible, that's shorthand for Alice can guarantee to successfully respond to the summons in the particular version of the task. Okay. So this started out as a way of trying to think of things that distinguish relativistic quantum theory from the other familiar, simpler theories that we have. So just to recap on that, suppose we're thinking about relativistic classical physics. Well, Bob gives Alice an unknown classical state, but of course it won't stay unknown. She can measure it up arbitrarily precisely. She can broadcast the description everywhere. Assuming perfect technology, she can reconstruct a copy of the thing anywhere she wants. So if he gives it to her at P, and he tries to surprise her by asking for it at Q, well, she's ready. She's got the broadcast description, she's got an agent there, she can instantaneously build it and hand it over.
I got a few questions. So he tries to surprise her by asking for it at Q. But, looking at the beginning, I had in my mind that the space-time points were all known in advance.
So yeah, you're right. So yes, but in this version of the past, so what's really happening is that Bob, there's a large or infinite number of points where he could ask for it back, and so there could be an input, just a single bit that has value 1 at one of those points, and a picosecond later, there's a return point just above that. But thanks for clarifying. Yeah, that's helpful. Okay. So there isn't really much to say about summoning in relativistic classical theories. It's always possible. Likewise, non-relativistic quantum theory. So if Bob gives Alice an unknown quantum state here, and space is going this way and time is going this way. Well, she could do all sorts of things. One thing she could do is just hang on to it at the same spatial location. And wherever the summons comes in, she's got an agent ready, and the agent can send instantaneously a message saying, hey, I need the state over here, and she can instantaneously respond and get the state over there. So she still doesn't know what it is, but she can give it back to Bob. So again, there's nothing interesting going on there. But there's something at least marginally interesting in relativistic quantum theory. So now Bob gives Alice the state at point P, and there could be an infinite set of points, but suppose even there's just 2 space-like separated points where he could ask for the state, and she knows perhaps that he might ask for it here, or he might ask for it here. Even in that case, if these are space-like separated, and if she's got to respond pretty quickly, well, whatever she's able to do or is not able to do over here cannot depend on whether the summons comes in over here, because that would violate faster light signaling. So if she is able to respond over here, that must be true even if Bob illegitimately asks for the state over here as well. But the same reasoning works the other way around. If she's able to respond over here, that must be true even if Bob illegitimately asks for the state over here as well. And so, for both of those to be true, she must be able to successfully respond at both places, and that violates no cloning. So, we have one of the more trivial theorems of relativistic quantum information theory, the no summoning theorem. In general, unless we say more about it, summoning is not a possible task. just as cloning isn't.
Just in
Please.
So she doesn't have to send it to both, right?
No, the task is defined so that it's okay for her to respond to. She should expect only one summons. She will either get a summons at Q0 or Q1. But if there is any strategy that allows her to be sure that she will be able to respond successfully if it's asked for at Q0, and also that she'll be able to respond successfully if it's asked for at Q1, that same strategy must also allow her to successfully respond even if Bob violates the conditions of the task and asks for it at both. Because of the faster light signaling. Whatever she's able to do over here can't depend on whether or not Bob's cheating over here, because if it did, there would be a way of sending signals from here to here. Is that?
So you said that if you have if she has a strategy to reply to any one of them, then she should be able to do
If she has a
simultaneous.
if she has a strategy that guarantees that she can successfully reply to one, assuming there's only one, then yes, that would logically imply she, given the no signaling principle, that she has a strategy that will allow her to reply to both. And that's not possible. Therefore, there can't be a strategy.
Am I the only one on this meter? And I don't want to work it out, but I don't understand. So why? Still, she will have to do only one of them, right? Because only one of them comes, right?
Well, so the question is, suppose Bob cheats.
Yeah.
Suppose that actually he does ask for it in both places. And suppose she's set up with this strategy that will work if he asks only in one place. Then the logic says, well, this strategy still must work on each side, even though Bob has cheated. But think about it a bit more. We can always go through it again.
Kind of generally complying, kind of ever.
Well, she can't. Yeah, it depends. I mean, it's not true for all configurations of call points. So it's not true when these are space-like separated. And she can't guarantee to comply. Of course, she can have probabilistic strategies, but
You can
yeah.
only comply with probability 1/4 just by teleporting the qubit from one place to the other with probability 1/4.
Sorry, you mean she could? What do you mean, actually?
Send it to Q0,
Yeah.
and then there is a Q0.
Yep.
And now she teleports it over to Q1 using a previously shared entangled LNAN.
When you say now, do you mean now Q0 or?
Yeah, just like a tiny second after Q0.
Yeah.
No, then Q1 just guesses what the classical message would be, and with probability 1/4 gets it right.
Yeah, well, I mean, she might as well forget about the teleportation, and Q1 just returns a random state. I see. There's a subtle difference here, yes. So one question is, what's the probability of her persuading Bob that she's succeeded? But you're asking for something slightly more platonic. What's the probability of her actually handing over a state that is psi, or will be psi?
That's what we don't know about.
I guess it is possible to send a state to another space-like separated place with probability 1/4 by quantum teleportation, depending on your interpretation of quantum mechanics.
Yeah, that last bit. I mean, what she actually has at Q1 in that strategy, if the state was at Q0, is just half a singlet, right?
Yes.
And then one could discuss half a singlet with a classical message that's going to come in later. So it's true she could just take a guess at the classical message. Quite what you say about the unitary applied to half a singlet is also up for debate, I think.
Yeah, I guess it depends whether you think the measurement she did at Q0 maps the wave function.
Yeah. Anyway, there's certainly probabilistic strategy. I mean, the simplest thing, obviously, she could at least take a guess as to whether it's going to go to Q0 or Q1, and half the time she'll be right. So people sometimes worry briefly about whether the problem is that we've just idealized the task. It's certainly true. You probably should make it more realistic if you're ever going to talk about implementations. So you should allow her a little bit of time to respond, or some window, some region in space-time, and you should probably allow her some error, so it'd be good enough to return a state with fidelity 1 minus epsilon, where epsilon is small. It doesn't really make, it in fact doesn't change the picture, as I think it's going to be almost it's obvious with a moment's thought, because we have bounds not just on exact cloning, but also on approximate cloning. It's not possible to approximately clone the state so that you've got two things that have fidelity close to it. Allowing a little time doesn't make any difference as long as the two regions are still space-like separated. Okay, so then you can think, at least if you're Patrick and Alex, you can think more deeply about summoning and try and find something new and interesting to say. And go back to this sort of this discrete task-based picture that I started with. So the version of the summoning of approximate summoning they introduced is still precise in the